Okay, so this is our first lesson in 2.2 graphing polynomials. Here's your warm-up. Pause your screen and quickly do these. So, factoring and very, very quick sketches. What you should get is factors out the GCF of x squared, then you have this quadratic you can just simply factor. Very quick sketches, x squared, if it's positive, both ends go up, negative, both ends go down. This is what x cubes look like, and if you reflect it, it looks like this. Remember how we write end behavior. As x approaches negative infinity, so that's negative infinity on here, we're looking at this end of the graph, and you'll see that y is going up to positive infinity, that's that one. And as x goes to positive infinity, we're looking at this end of the graph, and it's also going up. We have a look at this one over here. As x is going to negative infinity, here's negative infinity, we're going up to, y is going up to positive infinity. And when this number is odd, you will notice that the end behavior for the y's will go in opposite directions. When this is an even number, like 2, what it's doing in the y's on both the left and the right end of the graph, those will match. Okay, so the homework today, that's all detailed in Canvas, what you're supposed to be doing, which questions to do and which day. We have a quiz on Thursday. Make sure you've completed your homework and handed it in before the morning of the quiz. So let's first of all just review what we know. As you change, these have all got odd powers. Y equals negative x to the power 1, y equals negative x cubed, y equals negative x to the power 5. What difference does it make? Well, this is what your graph of y equals negative, the negative is not really showing there, x to the power 1 looks like. It just cuts straight across at the origin, and we've just graphed y equals negative x cubed here. So notice what these points have in similar. They both go through the origin when x is negative 1, y is positive 1. When x is positive 1, y is negative 1. So they intersect, those graphs intersect those points. So that can help us imagine what y equals negative x to the power 5 is going to look at. If we put in negative 1, we're still going to get 1 out. If we put 0 in, we're still going to get 0 out. If we put 1 in, we're still going to get negative 1 out. But how the graph actually behaves between those points will be different. This is what it'll look like. You'll notice that the higher the power of x, the steeper the graph gets at the ends. But between negative 1 and positive 1, it actually kind of gets flatter. There's a wiggle in the x cubed and x to the power 5 graphs. This one, x to the power 1, just goes straight across at the x-intercept. These two wiggle. The bigger the power of x, the more pronounced that wiggle will be. Now, this will help us to graph something like this. You go, no, I can't graph that. I have no idea what an x to the power 4 graph looks like. Well, yes, you have actually. You take this into account, it's going to look almost the same as if we were graphing this with negative x squared. So it's going to basically be similar, just steeper, flatter, similar, but it's negative, so this end's going down and this end matches, because that's an even number. All we have to do is work out where that vertex is going to move to, and the vertex is going to move left 1 and up 1. So we go left 1, up 1, then it's probably going to go through that point there. 1 to the power 4 is still going to be 1, negative 1 to the power 4 is still going to be 1, and we've reflected that down. So our graph is simply going to look like it's a very steep, kind of flat in the middle parabola. Okay, I need to put those points so it's obvious where that vertex was. Okay, so we can graph that, just knowing that x to the power 4 is going to have similar end behavior, similar behavior to x squared, just a bit steeper. Okay, so you're on your own, you're watching video, you're not going to discuss with anyone, or people will think you're a nutter if you're talking to yourself. What do you remember about how to graph a polynomial such as this? Well, let's first of all remind ourselves we've been given two different forms of the equation here. This form here is expanded or general form, when it's all written out as separate terms. So that's this form here. And this form here, what we have been given is in fully factored form. General form is great for one thing, and one thing only. General form is great for finding out what your leading term is, which can help you easily find your end behavior. That's your leading term. Remember, your leading term is the one with the highest power of x. Sometimes we fool you and we don't write it at the front. We hide it amongst the others. But it's not very good for graphing. Fully factored form is much better for graphing because from this, we can tell where the zeros are. And if the zeros are real, then the zeros will all give us an x-intercept. For instance, this gives me zeros at x equals 0, x equals 3, and this one gives me an 0 at x equals -6. All of those are real, so they're all going to give me x-intercepts. There's a subtle difference between zeros and roots and x-intercepts. You only have an x-intercept if your zero root is real, not if it's complex and has an imaginary part. Okay? And you do exactly the same math to find them all. The only difference is, for instance, these are zeros. They're going to represent x-intercepts at the point. This one's at 0, 0. This one is at sort of x is 3, y is 0. They're just a point. You're doing the same math to work them out. You just write them in a different way. So if I try to graph that now, I know I have a 0 at x is 0. At x is 3, 1, 2, 3. I've got another 0 there, another x-intercept, because it's a real 0, and another one at -6. 1, 2, 3, 4, 5, 6. Oops. So I have one here. I know from my leading term that it's basically the graph is going to behave in the far huge values of x. These other terms are going to be negligible. It's going to behave like an x to the power 4 graph, and it's positive at the front. So it's going to be going up on this side and up on that side. If I hadn't seen the expanded form, I don't want to multiply all that out. I could have worked this was x to the power 4 by multiplying together all my x's. X squared times x to the power 1 times x to the power 1 gives me x to the power 4. Okay, so I know my end behavior would look like that. Now, if I just graphed it, and I've got these x-intercepts, and I know I'm going to start up over here, and I'm hoping to finish over there, because that's what this little planning sketch tells me. So I go through that one, through that one. Oh, that's wrong. I'm not very happy. What happened? Why is it wrong? It's because I hadn't considered this. Remember, there's more to it than just finding the x-intercepts. You have to work out how the graph is going to behave at those x-intercepts by considering multiplicity. Multiplicity is how many times a factor repeats. This one has multiplicity of 2. This 0 has multiplicity of 1. This 0 has multiplicity of 1. So it's not going to behave how I just drew that on that graph there. Let's just undo everything I wrote there. Oops. What it's actually going to do is this graph, I'll go over y in a second, is going to cut there, bounce there, cut there, and then it'll go off. Now I'm happy, because this end I was expecting it to go up because it's based on the end behavior of x to the power 4, and it is going up. So I'm happy now. But we have to go through why it does that behavior. So let's take some notes. First of all, your end behavior is based on the leading term test. So we just need the leading term. Our polynomial could be huge. It could be y equals 2x to the power 11 plus 3x to the power 9 minus 57x plus 2 million. I don't know. All we want is the leading term. So if your leading term regardless if it's positive or negative. If it's an even number, you're going to see a certain sort of behavior, and if it's odd, you're going to see a different sort of behavior. So the first thing you actually look at, let's give an example here. We'll do a positive one. Say our leading term was 3x to the power 10. This is even. I'm not looking at that coefficient. I'm looking at the exponent. That is the degree of my polynomial, how big n is. N is the exponent. If that's even and positive, the positive means it's going to end on the far right going up. And because it's even, both ends are going to match. It's going to look like this. If I had another polynomial that was negative 5 x to the power 6. Again, the exponent is even, so both ends will match, and I know which way they're going to go because I know the far right side is going to go down. So this one would look like that. And for odd, depends if it's plus or minus. Let's write an example. Say I had a leading term that was 4 times x to the power 11. It's odd because I'm looking at the exponent. I'm not looking at the coefficient. I'm looking at the exponent. If it's positive, it's going to end high up on the right. And if it's odd, the ends will go in opposite directions. If this ends high on the right, because it was positive, because it's an odd number, the other side must go in the opposite direction. And one last example, if I had 2 times x to the power 99, that's odd. Ooh, that's supposed to be an exponent, should be written small. But if this was negative, then this side wouldn't be going up, it'd be going down. And the other side, because it's odd, is going to have to go the opposite way. So it'd look like this. So when you're looking for end behavior, please don't look at odd or even first. Please look at the plus or minus first, because what that tells you, let's get a narrower, thinner line, please. Let's get a narrower purple line. If you look at this first, that tells you what the right side is doing, whether it's going up or down. Okay, what the right-hand side is doing. Then you look to see if it's odd or even, and that tells you whether, if it's even, both ends go the same way. If it's odd, they go in opposite directions. Odd, opposite directions. Okay, so work these out. Pause your video and finish these off. Going over them in 3, 2, 1. On this one then, here's your leading term, 3x to the power 4. So your leading term is 3x to the power 4. This one you've got positive, even. So your end behavior will look like this. Now, if we ever ask you to write out, to describe the end behavior, we'll ask you to describe it. We want more than this grotty little sketch. We actually want to write it out like this. As x approaches negative infinity, so this is negative infinity on x, we're going up. The y's are going up to positive infinity, and the other side is also going up. They're both going up together. And this was our trick question. Did you get that it's positive odd? No, I got it negative even. Well, that's because we tricked you. Look, 2, 5. This is our leading term, not that one. Okay, we will trick you with things like that. So because it's positive, odd, positive, it's going to end high, odd, the other side will be down. So as x goes to negative infinity, we're talking about this end, and this end is going down. Y is going to negative infinity. As x goes to positive infinity, here's positive infinity for x. So I'm looking at this end, it's going up. And this one, there's your leading term, negative, odd, looks like that. So because it's odd, these are going to be different. And because it's negative, the one as x goes to positive infinity, that's your right side, will also be negative. It's going to end up with a negative because it was negative. Moving on. So the behavior at the zeros. Does your graph bounce, wiggle, or cut across? Remember, if zeros are, the roots of the zeros are real, they're going to actually give you your x-intercepts. So what we're talking about when we're talking about behavior at zeros, we're talking about what the graph will look like at the x-intercepts. Okay? Oops, spelled that wrong. Okay? How you work it out, you need to look at the multiplicity. It's all about the multiplicity of each zero. You want to see if that multiplicity is an even number or if it's an odd number that's bigger than 1 or an odd number equal to 1. So first of all, let's talk about what multiplicity is. Well, multiplicity is not this number. It's not what's inside the parentheses with x. Multiplicity is the power the factor is being raised to. It's the number of times a factor repeats, or a zero repeats, or a root repeats, okay? So this is repeating 4 times. This could have been written as x minus 5 times x minus 5 times x minus 5 times x minus 5, repeating 4 times. So this has a multiplicity that is an even number. And if your multiplicity is an even number, then the behavior you're going to get is it's going to bounce. Now imagining a ball bouncing off a table. Does it bounce on it and go through? No, it bounces and turns around. It hits the table and bounces back up again. So imagine here that this was just part of a polynomial that had many other factors. So that's not the only zero. This particular zero is going to give us an x-intercept at x equals 5. And because this factor has got a multiplicity that's an even number, it's going to bounce. We're going to get the graph bouncing at x equals 5. Now I've sketched this one in for you. That's x is 5. See, count these. 1, 2, 3, 4, 5. That's a bounce. See, it hasn't crossed from one side to the other. Now I've just sketched that coming from underneath. Depending on where you were in the flow of the graph, it might have been coming down to that point, bounce off the table and go back up again. So considering these other factors, maybe the graph had been coming along, maybe it done a wiggle there, and you're coming there, and it's going to bounce. Now, how to bounce nicely? Can you see, if I kept on going in a straight line, I wouldn't hit that point. To bounce nicely, aim a little bit to the side. So I'm aiming to something a little bit to the side of it, and that gives me room to turn around and get a nice smooth bounce as opposed to a jagged thing. Okay, right. Now, if your multiplicity, we're looking at the multiplicity, so that's the power of the factor, the number of the times the factor repeats. If it's an odd number, if it's greater than 1, like 3, it's going to wiggle. If it equals 1, it's going to cross, just cut straight across, okay? Now, when you wiggle or cut across, you do go from one side of the x-axis to the other. You don't bounce and come back. You cross over to the other side of the x-axis. So this one is going to give me a 0 at x equals 5 again, but this time the multiplicity is odd, and it's a number bigger than 1, so it's going to wiggle. And this is what a wiggle looks like. Where's the one I prepared earlier? I know I've got one here somewhere. Ah, there you go. So the graph could have been coming along, and again, to wiggle, notice how again I am missing where I'm aiming for. I'm coming in as though I'm going to hit this value, not that value, and then at the last minute you go flat in the middle. You don't go vertical, you go flat. I see some horrible attempts at wiggling. I see things like this. When people go like that, that's not a wiggle, they went vertical. And look, it's only got one change of curvature from opening down to opening up. This has got like 4 changes of curvature. This is not a wiggle. That's a wiggle. Okay. And this one. If it's odd and exactly equal to 1, it's still going to go across the x-axis. See, it crossed from below to above, or it could have been coming from this way and wiggled like that. It's going to go from one side to the other, but if it's got a multiplicity of 1, then it's going to just cut straight across in a straight line like this. Let's put all this together and try and graph this. Well, at the moment, I wouldn't expect you to be able to, well, this would be a function first to be able to graph it. This would be, in general form, yuck. I have factored it for you. By next week, we'll be able to factor things like that, you know. That's a scary thought, isn't it? So this is supposed to be the number 2, but it didn't write very well. This is it when you factored it. What do you notice? There's really only 2 factors. This x minus 3 factor is repeated once, 2 times, 3 times. This could have been written like this. So now this has got a 0 at x equals 3 with a multiplicity of 3. When the multiplicity is 3, an odd number bigger than 1, it's going to wiggle there. That one cut. Okay. This one has given me a 0 at x equals negative 2. It's what's being subtracted. Set that whole thing equal to 0 and solve it. X negative 2 plus 2 would give me 0. So x is negative 2. We've got a multiplicity of 1. It's just going to cut across there. So let's try and have a go at graphing this. At x equals 3, this multiplicity is an odd number bigger than 1, so I'm going to wiggle there. I'm going to wiggle there. And at x is negative 2, it's got a multiplicity of 1, so it's just going to cut straight across. At negative 2, I'm going to just cut. So I put a little c to remind myself. So I don't have enough information yet to graph it. I've got to look at my end behavior. We're going to pretend we didn't see that because that's giving it away. This is the bit a lot of students don't know how to do, so we'll go over it one more time. To find your end behavior, remember it's all based on the leading term test. So we need to know our leading term. That's the highest power of x. It's not just this x cubed. In factored form, you have to multiply all your x's together. So I'm multiplying, and it's got positive outside, so I know it's plus. I've got x cubed times x to the power 1. Oh gosh, that cube's awful. Remember, when you're multiplying bases with an exponent, you add the exponent. So this is going to be x to the power 4. So it's positive, which means it's going to, this is my little planning sketch. It's going to end up, that's an even number, so both sides will match. So I'm hoping I'm going to start there and I'll end up finishing there. Let's graph it in. Cut across, got a wiggle. So I'm not going to aim straight for that. I'm going to aim about there. Go flat and wiggle out. Yeah. And I'm happy because it ended up opening where I was hoping it would from my little planning sketch, which here, yeah, I was hoping it'd end up and it did end up. So I'm happy. Now, if my planning had made me think I was going to go down there, please never ever throw in an extra intercept. Please, if you end up pointing up and you hoped you were going to end up pointing down, just put a sad face. Do not do this. Do not say, oh, I've got to end up down. I'll sneak that in. Because if you've done that, you've just added an extra x-intercept. And that would have meant there was another factor on the end here, such as something like x minus, well, if that was like 5. And you've totally and utterly changed what you've graphed. You can't do that. Never, ever, ever do that. You're going to lose less points by just saying, oh, it's pointing the wrong way and drawing a sad face for me, okay, than throwing in an extra x-intercept. Right, there's one more thing on this graph that I could check. Notice how I've put some indication of scale on the x-axis, but on the y-axis, I've done no indication of scale at all. That's because we don't really know how low that lowest point is. We don't even know that the lowest point is on the y-axis there. I made that up. It could have gone down here and then wiggled there. Yeah, this could be the lowest point. To work out what your y-intercept is, your y-intercept is simply when x is 0. So I've got 0 minus 3 cubed, which gives me negative 3 cubed, which has to be multiplied by 0 times 0 plus 2, so 2. So my y-intercept is at negative 27. That's my negative 3 cubed times 2. This is at negative 54. Do we want to put any indication of scale on the y-axis? Oh, heck no. I don't want you counting down negative 54 lines. That would be madness. And don't forget, this bit wasn't part of my actual question. was just saying don't do that if your planning sketch is wrong. Okay, so let's give you some to practice. So you try those, pause your video, do them, and I'll go over them in a second. So here we go. On this one, your leading term is x to the 1 times x to the 1 times x to the 1. X to the 1 times x to the 1 times x to the 1, which is x cubed. And it's not going to minus at the front, and none of these are reversed with a negative. If we'd revert, we're not going to do that to an academic. This is a positive odd leading term. The positive tells me it's going to, on the right, it's going to go up into quadrant 1. The fact it's odd means that these ends are going to go in opposite directions. This one's very boring because all of my zeros have got multiplicity of 1. So they're all going to cut across. This gives me the 0x is -1. This one gives me the 0x is 5. This one gives me the 0x is -3. And they're all very, very boring. I'm just going to cut across at each of them. So let's do this in a different color. At x is -1, I'm going to cut. Oh, that should be a solid dot. At x is 5, I'm going to cut. And at x is -3, I'm going to cut. Planning my graph, I'm going to start down. So I'm going to start down here and hope that I end up over there. Let's try. So cut, cut, cut. Oh, look, I wrote 3 there instead of a C. That was -3 as well. Okay, so am I happy? Yes, I was expecting it to end up, and it has ended up. You don't have to put the smiles on your graphs. This next one is a much more interesting one. Let's have a look at this. So let's first of all have a look at our leading term. We've got x cubed has to be multiplied by x squared, has to be multiplied by x to the power, oh, nothing's written there. What is it? It's a 1. So we've got x cubed times x squared times x to the power 1, which gives me x to the power 6. So this one, again, is positive. It's going to end high because this is an even number. The ends are going to match. It's going to start high as well. Okay, let's clear off that junk I wrote on there. And let's have a look at zeros. This gives me a 0 of x is 0 with multiplicity of 3, which means it's going to wiggle. So at x is 0, I'm going to have a 0, and it's going to wiggle as it goes past that. So when it wiggles, don't forget, it's going to go from one side of the x-axis to the other, but I don't know which direction it's going yet when it hits that one. Then I've got this one gives me x is -4, 0x is -4. Its multiplicity is 2, which is an even number, so it's going to bounce. So it's going to bounce here. And this last one gives me x is +3, and its multiplicity there is 1. So that one's simply going to cut across there. That's going to be a cut. So let's draw our graph. Let's get a narrow, I prefer the narrow line, I think. So I'm going to start up high over here, and I'm going to hope that I'm going to end high over there. So bounce. Remember, when you bounce off a table, you don't go through to the other side. So bounce, bounce there, wiggle. Remember, I'm aiming slightly to the side, go flat, wiggle down, and just cut straight through. Yes, I'm extremely happy because that ended up, and I was hoping it would end up. Oh, I'm missing the arrow on this end. Okay, now let's have a look at these graphs. These are neater ones that I did actually drawing properly on a board. Let's talk about them. Now, I've drawn what's supposed to be a happy person there. You don't have to draw that on your graph, but think about it. Have you ever seen anyone walking down the street with a head that looks like that? Don't be ridiculous. Of course you haven't. That is a caricature of what a happy person looks like. That's what we want you to graph. We want you to graph a caricature. Our sketch is a caricature of what the real graph looks like. By the way, I didn't work out this. Where would my y-intercept be on this one? 0 plus 1 is 1. 0 minus 5 is minus 5. 0 plus 3 is 3. Multiply those all together. That's what you're doing here. And you've got negative 15. Okay. So this y-intercept is negative 15. See, I've got a clearly marked scale on the x-axis, no scale on the y-axis, and they do not all go through the origin. They only go through the origin if you've got a factor that's just a single x like that. Yeah? Okay, so that's what the caricature, that's what we're graphing here. In reality, if you put that in some graphing app, you'd get this. So I can tell if you're cheating in a test. If you graph me something like that, you don't know how far down it goes yet or how far up these minimums and maximums are. We learn that in calculus. You don't know how to do that yet. Okay, and the next one's even worse. This is what I want to see. I want to see a graph that looks like that, where I can clearly see both ends are going up, and I can clearly see you're bouncing, and I can tell that's at negative 1, 2, 3, 4. I can clearly see a wiggle here at the origin, and I can clearly see you're cutting across there. That's what I'm looking for, and it should be really clear. If you put this in a graphing application, this is what you'd see. I don't want to see that. That tells me for sure you cheated. Look at this red line. You can't tell which end. Is it going up or is it going down? You can't tell. Well, that's probably going down, so it probably connects there, it probably goes there. But if you draw me that, I know you've cheated. I know you've put it into a calculator or a graphing app, and that's not what I want. In fact, if you wanted to see the rest of this graph, if you zoom out, that's what it looks like. My goodness, look at it. This is telling us, look here. Can you see that point there? That's this turning point. And it's happening at almost 200. Let's call that 190, approximately 190. This down here is this minimum here, and it's happening at negative 340 about. Okay? Please keep the caricature. And you're not going to be able to work those out yet. That's something you learn how to do in calculus. I just want to see this caricature of the graph. Okay. Let's stop this video and we'll produce another one for the rest of the lesson.